Hello all. The objective of this video is whenever the impulse response of the system is given, how do you check whether that given system is static, causal or stable from the impulse response. Say, the first example, let us consider a discrete time LTI system whose input is x of n, output is y of n, and the impulse response is h of n. In this case, the h of n is given to be alpha power n into u of n. They have not given what is the value of alpha here. And then from this impulse response, we should check whether it is static or not, causal or not, stable or not. Now, since they have not given the value of alpha, alpha could be anything. Alpha could be greater than 1, less than 1, but what we will assume is the given problem will say that alpha is a real number. Okay, we'll assume that. So alpha can be greater than 1 or less than 1. If alpha is greater than 1, then of course the diagram is shown here. When it is alpha is greater than 1, it's a growing exponential sequence. When alpha is less than 1, it is a decaying exponential sequence. Since u of n is there, u of n is defined as a function which exists only for positive time index or for n greater than or equal to 0, and it will be 0 for n less than 0. That is why you can see that for -1, -2, -3 and so on, the impulse response doesn't exist for any values of alpha. Now let us check when it is said to be static. Now if you recollect from the previous video, we had said that the LTI system is said to be static if h of n is of the form c into delta of n, c into delta of n. Now that is, it should be in the form of an impulse function. Now from the above figures you can clearly see that the figures or the impulse response doesn't represent an impulse function. It is nowhere looking like an impulse function, and hence we can say that the given system is not static, but it is dynamic. It is dynamic. Okay, fine. Next, when can we say that system is causal or not? Now, if you recollect, the system is said to be causal if h of n is equal to 0 for n less than 0. Now if you observe the previous figure, it is clearly observed that in both the cases the impulse response is 0 whether alpha is greater than 1 or alpha is less than 1. H of n is 0 for n less than 0, and hence we can clearly say that from the figure that the given system is causal. Now, last condition, when can you say the system is stable? Now, if you recollect from the previous video, we had discussed that summation n is equal to minus infinity to plus infinity, h of n should be less than infinity. That is, if I sum all the components of the impulse response, it should give me a finite number. That is, it should be an absolutely summable. Only then I can say that it is a stable system. Now if you see that in applying that formula here, now summation, now since the in the given problem the impulse response exists only from 0 and not from minus infinity, we can change the limit as from n is equal to 0 to infinity, and for that value it is alpha power n. So it is alpha power n. Okay, now here we can clearly say that this will be equal to 1 by 1 minus alpha, provided the magnitude of alpha is less than 1. That is, it will converge to a value of 1 by 1 minus alpha if magnitude of alpha is less than 1. What if magnitude of alpha is greater than or equal to 1? Even if it is equal to 1, it will be a diverging sequence. It is a growing exponential sequence, and hence it will be equal to infinity and not a finite quantity. Hence we can say that the given system is stable provided the magnitude of alpha is less than 1. Hence in this problem the given system is dynamic, and then causal, and then stable. Okay, let's see another example. Continuous time system. whose input is x of t and output is y of t, and impulse response is h of t, which is given as h of t is equal to e power minus 2 mod t. And for this system, by observing the impulse response, we should check whether it is static, causal, or stable. Okay, now before that, let me clarify what is mod t equals to. The mod t is equal to minus t for t less than 0, and it is equal to t for t greater than 0. Now the above problem can also be asked like this, that is h of t is equal to e power minus 2 mod t, or it can also be asked as it is equal to e power 2t for t less than 0 on e power minus 2t for t greater than or equal to 0 by using the definition of mod function. Or we know that t less than 0, that is an u of minus t function, and when I say t greater than or equal to 0, it is u of t function. Hence h of t can also be equal to e power 2t into u of minus t plus e power minus 2t into u of t. Now how does this function look like? Now the function is looking like this for t greater than equal to 0 and for t less than 0, and the function is symmetric with respect to y-axis, that is at t equal to 0. Now for this function, let us check whether it is static or not. So now again we know that the given system is static for a continuous system if h of t is in the form of c into delta of t. Now it is clearly noted that the given function is not in the form of c into delta of t, and hence it is dynamic. The system is said to have memory. The given system is dynamic. Okay, now let us see whether it is causal or not. What is the condition for the causality, causal, for system to be causal? That is h of t should be equal to 0 for t less than 0. Now you can clearly see that the impulse function exists for both positive values of t and negative values of t, and hence h of t is not equal to 0. In this case, h of t is not equal to 0 for t less than 0, and hence the system is said to be non-causal. Okay, let us check whether the system is stable or not. Okay, for the system to be stable, it should be absolutely integrable. That is, for t is equal to minus infinity to plus infinity, if I integrate it, h of t with respect to t, it should be less than infinity. Now substituting for the given problem, in the given problem we can split, that is from minus infinity to 0. For t ranging from minus infinity to 0, it behaves as e power 2t, and for t ranging from 0 to infinity, for t ranging from 0 to infinity, it behaves as e power minus 2t. So using this diagram, I can rewrite this as, so from minus infinity to 0, it is e power 2t dt, plus from 0 to infinity, it is e power minus 2t dt. Now evaluating this integral, it is a simple integral, e power 2t by 2 from minus infinity to 0 plus e power minus 2t by minus 2 within the limit 0 to infinity, and substituting it, this gets e power 0 is 1 by 2 is half, e power minus infinity is 0, so this gets evaluated to half, plus e power infinity by substitute, here minus is there, e power minus infinity is 0, 0 minus e power 0 is 1, 0 minus 1 is minus 1, minus is already there in the denominator, minus 2, minus would get cancelled, so it is again half, and it is equal to 1. So half plus half is equal to 1, which is a finite quantity and obviously less than infinity. The condition is satisfied, and hence the given system is stable. Now in this problem we can see that the given system is dynamic, okay, and the given system is non-causal, and the given system is stable. Now we'll see another system. Say suppose the impulse response of the system is given to be, say, h of t is equal to delta of t plus 1. Okay, Now we'll check whether this given system is static or dynamic, or it is causal or non-causal, stable or not, or it is invertible or not. We'll check the four conditions. Now if I draw the diagram for this t, h of delta of t plus 1. Delta of t plus 1 means delta of t shifted to the left by 1 time unit. So this is 0, this is minus 1, and area under that function is 1. Okay. This is the representation of h of t. You can clearly see that is h of t in the form of c into delta of t? No, it is in the form of delta of t plus 1. Therefore, the given system is dynamic. Okay. Is h of t equal to 0 for t less than 0? No, the function exists for t less than 0 and hence it is non-causal. Is it absolutely integrable? Yes. If I integrate it from minus infinity to plus infinity, delta of t plus 1 dt, if I integrate it, obviously area under the impulse function, I am considering the limits from minus and plus infinity, definitely it will be equal to 1, which is less than infinity, a finite quantity, and hence the given system is stable. Okay, the given system is stable. And invertibility, what is the condition for invertibility? The condition for the invertibility is that h of t, okay, h of t convolve with h inverse of t should be equal to delta of t. That is, h of t convolve with h inverse of t should be equal to delta of t, where h of t is the given system impulse response, h inverse of t is the impulse response of the inverse system, that should be equal to delta of t. Now, is this system invertible? How can we know? We know h of t. We have to obtain, can we obtain h inverse of t? Now, here I have delta of t plus 1. Here that should be equal to delta of t. Under what conditions will I get this? When I convolve delta of t plus 1 with delta of t minus 1, only then I can get delta of t. This is from the property of convolution integral for direct delta functions. That is, delta of t minus t naught convolve with delta of t minus t1 is equal to delta of t minus t naught minus t1. Okay, using this you can see that here we have it is plus 1, here I have used minus 1, and if I substitute this I get which is equal to delta of t. Now clearly the given system, this system is invertible and thus in impulse response of the inverse system. So the arrangement would look like this. This is h of t, which is in the form of delta of t plus 1, and if the here is x of t, and here I get y of t. Now if I give the output of this to a system whose impulse response, say h inverse of t, which is equal to delta of t minus 1, then I'll get back my signal x of t, and hence the system is invertible. Yeah, thank you.